the sun will find me walking down this broken path.
Welcome. This video introduces the hydrostatic equation, shows an example, presents a derivation, and summarizes some of the key ideas. Let's get started. Overview. Go to table F.2, commonly used equations. Scroll down to the hydrostatic equation. Notice there are three forms of the equation. These are all the same. You can do algebra to get from one form to another. Terms. P is pressure, gamma specific weight, Z is elevation. Delta P means a change in pressure. Delta Z means a change in elevation. Example problem. What is the pressure at a depth of 20 meters? Assume seawater because we saw coral in the photograph. Locate point 1 at the free surface, point 2 at a depth of 20 meters. Our goal is the pressure at depth 2. And we all know from our everyday experience that as we dive from 1 to 2, the pressure will increase. And this is due to the weight of the water column above us. To characterize weight, let's look up the specific weight of seawater. So this can be found in table A.4. The value is 10,070 newtons per cubic meter. So again, that's table A.4, and that value is at 10 degrees C and 1 atmosphere. The hydrostatic equation, let's use this form. Delta P equals minus gamma. Delta Z, we'll subscript that for seawater. We want to find how much the pressure increase is. This is a change in elevation, that's 20 meters, and we've looked up that value already. And the way I like to think of this equation is just putting an absolute value there, because we know that as we go down in depth, pressure will always go up. And so we can go ahead and run calculations. So this is 10,070 newtons per cubic meter. Okay, the calculation shows that the pressure increase is 201.4 kPa. This means physically that the pressure here is 201 kilopascals greater than the pressure here. Since the pressure here is 0, in a gauge pressure sense, we can say that the pressure at 2 is 201.4 kPa gauge. End of problem. Derivation, hydrostatic equation. Step 1, setup. Define an arbitrary body of fluid. Identify point 1 and point 2. Identify a fluid particle at an arbitrary location. Assume hydrostatic conditions, then the hydrostatic differential equation applies. Step 2, integrate. Take the dz to the right side of the equation, the gamma to this side. We're doing separation of variables. So dp over gamma equals minus dz. Integrate both sides of this equation. Let's do definite integrals. So the pressure varies from P1 to P2, while elevation varies from Z1 to Z2. The integral of dp is P, and taking the limits, we get P2 over gamma minus P1 over gamma. The integral of dz is Z, and taking the limits, we'll have Z2 minus Z1, but we have a negative sign, so we can write that as Z1 minus Z2. All that's left now is algebra. Taking the pressure term and the elevation term and combining them, they're both positive, we can write P1 over gamma plus Z, then P2 over gamma minus Z2, that comes over and that's positive, we'll write it on the right hand side. P2 over gamma Z2. That's the final result. That's the hydrostatic equation. Step 4, interpretation. Here's the hydrostatic equation, and points 1 and 2 are arbitrary, so we could have picked any points, but what we have here is a constant. And so we can see that this collection of terms equals this collection of terms is equal to a constant. So regardless of what points we pick in the body of fluid, this collection of terms is constant. And we call this collection of terms piezometric head. It's given the symbol H. In other words, H is defined as P over gamma plus Z. So the interpretation of the hydrostatic equation is that piezometric head is everywhere constant in the body of fluid. So if we come to our original situation diagram, the piezometric head at location 1 and location 2 are exactly the same. If we pick another point, the piezometric head here will be the same. Another point, the piezometric head here will be the same. This provides a very easy way to solve problems. And the only assumption we made in deriving this is that gamma equals constant, and we made this assumption to pull gamma out of the integral. And we can also write gamma equals rho g. So if gamma is constant, that's another way of saying we're assuming the fluid density is constant and the gravity field is constant. End of derivation. Summary: hydrostatic equation. Two key assumptions: fluid density is constant. Second assumption is hydrostatic conditions prevail. And recall that this means that the weight of the fluid particle is exactly balanced by the net force of pressure. The most common form of the hydrostatic equation is the head form. P over gamma is pressure head, Z is elevation head. The sum of pressure head plus elevation head is called piezometric head. And the key idea is the piezometric head is constant in a hydrostatic fluid. The meaning of the head form: just simply pick any 2 points and you can say that the piezometric head is constant. Go ahead and solve your problem. In the pressure form, we relate the pressure change to gamma times the change in elevation, or density times the gravitational constant times the change in elevation. Physics: the pressure increase from point 1 to point 2 is simply gamma delta Z. And we always know pressure is increasing as we go down in fluid. How to apply the hydrostatic equation? Step 1, check your assumption. Step 2, select points 1 and 2 where you know information or where you want to find information. Go ahead and label these points and label your datum. So for example, down here, point 1 was selected at the free surface because we know the gauge pressure there is 0 and we know the elevation. Point 2 was selected down here because this is where we want to solve for pressure. Notice that the datum is sketched. Step 3 is write the general form of the hydrostatic equation and then do a term-by-term analysis. Step 3 and 4 look like this. Here's the general form of the hydrostatic equation, and here's the term-by-term analysis.